All right, so the next part of the differential equations that we're going to look at are the slope fields, and this is the graphical form of a differential equation. So let's go ahead and get into this here now. So like I said, these are graphical representations of differential equations, and if you remember when we did, which you should remember because it wasn't that long ago, when we did definite integrals of a function, we always wrote it as, we found the integral of the function, and then we had a plus c. That plus c is because you could have a constant at the end that is different, and all constants have the same slope when we do the derivative. They all have the same derivative of 0. So when we had the plus c at the end, what that meant was that there were multiple, you can see the 6 different color graphs over here. There are multiple graphs, infinitely many graphs actually, that would have the exact same derivative. So when you're going from a derivative to, when you're going from a function to a derivative, that is a pretty concrete derivative. But when you're going from an integral to, working backwards, then the antiderivative, you could have multiple functions that give you the same derivative, and that's why we had that plus c. Okay, so this is what the slope fields are representing. And basically, what we're going to do is we're going to draw these by drawing like little lines, and I'll show you what I mean here in this first example. So a lot of AP tests will have a slope field in the free response where they'll give you, they don't give you as many points as what I have here. They usually give about 6 or 9 points. You can see here that I have 5, 10, 15, 20, 25 points. There's a lot of points. They'll usually stick to a size about like this, just because they do take some time to do. But I figure if we do a lot more, then doing a few of them should be easier. So what we do then is, typically when we were graphing lines before, we would just plug in numbers for x and we would get an answer for y. But what we're going to do now is each of these points has an x and a y coordinate. So like for example, if I start here at the origin, that point is 0, 0, which means the x coordinate is 0 and the y coordinate is 0, so the derivative there is 0. So that means I need to draw a little slope here of 0, which is just a flat line. So right there at the origin, I'm going to draw a flat line to represent the slope of 0. Now, you'll notice a pattern here, and basically, where is this equal to 0, x minus y? And that is wherever the x and the y coordinates are the same. So if I have the point 1, 1, 1 minus 1 would be 0. So here's the point 1, 1, so if I draw my slope there, that would be 0. And then also up here at 2, 2, down here at negative 1, and negative 2, negative 2. Okay, so if you notice the pattern, you don't have to plug in all the numbers, you just follow the pattern. Okay, but you can plug in the points and see what you get. Okay, let's move on to another one. This point right here, this point right here is the point 1, 0. So let's plug that in and see what we get. So if I plug in 1 for x and 0 for y, my slope is 1. Now use your points to help you, estimate what is the slope of 1 look like. So from algebra 1, we know that means go up 1 over 1. So we would have a slope that looks like this. Now where else do we have a slope of 1? Well, that's going to happen anytime the y coordinate is 1 unit less than the x coordinate. So for example, the point 2, 1. So we go to the right 2, up 1. This would also have a slope of 1. Okay, also at 0, negative 1, we would have a slope of 1. So 0, negative 1 is right here. And you can kind of see that all of these on this diagonal here would have the same slope. Now, when you are doing these problems on your AP exam, what they are doing is they are going to look and see, how does this slope compare to other slopes? So if I end up with a slope of 2, so let's say if I use this point right here at 2, 0, so the point 2, 0 has a slope of 2, what you need to do is, we know that these had a slope of 1, so this having a slope of 2, it needs to be steeper than this one. And that's what they're looking for, is in comparison to the other points, are you showing that it is steeper? But the other thing you can do is start at this, so we can go down to over 1. So I know I need to have a slope that kind of looks like this. Okay. Also at the point 1, -1, I have a slope of 2. So that would be right here. So again, we're going to make it look similar to this slope right here because they have the same slope. Same thing down here. So we want to make those three all look the same. Next, the slope, I'm sorry, the point 2, -1. So 2, -1, 2 minus -1 would give me a slope of 3. And again, in comparison to this one, I need to show that it is steeper. Same thing, this one would have the same slope. So again, we got to show that it is steeper than this slope of 3, or than this slope of 2. And the last one down here would be the point 2, -2, which if we plug in 2, -2, we get a slope of 4. And again, in comparison, we need to show that it is steeper than the slope that was 3. All right, now let's come up here to the top section and plug in some of those numbers. So let's see what we get up here. So let's say the point is 0, 1. So if x is 0 and y is 1, I got a slope of -1. So -1 means down 1, right 1, so I would have this right here. What if I plug in the point 1, 2? This point, 1, 2. 1 minus 2 gives me, again, -1. So you can see that all the points on this diagonal have the same slope. -1, 0 has a slope of -1. And -2, -1, -2 minus -1, you can see that that also has a slope of -1. Next, let's go to the next points here, the next diagonal set of points. And you'll notice sometimes all the ones in a horizontal line have the same slope, sometimes the ones in a diagonal this way, sometimes in the ones in a diagonal this way. Sometimes there's no pattern, and it's more, I should say that, not that there's no pattern, but it's more difficult to see the pattern. All right, so the next one here is 0, 2. If I plug in the point 0, 2, I get a slope of -2. Again, show that it is steeper than this slope of -1. Down to over 1 would be something like this. Same thing for these ones here. We're going to show that they have a slope of -2. Next, this point right here is -1 for the x-coordinate minus 2 for the y-coordinate. So that is a slope of -3. All right, so again, just like before, we're showing that this is steeper than the previous one. So there's -3, we'll call that -3, and then this one is -4. We don't want to draw a vertical line, so make sure that it is not vertical. But and sometimes what we need to do is we need to say, all right, well, if that's my slope of -4, that might not look like it's steeper than this one, so we may have to come back and do a little erasing. Okay, so this one I would say something like this maybe. So you may have to come back and erase some to show that it is steeper or less steep than a previous slope. Okay, so that is going from a function, a derivative function, to a slope field. So this, like I said, maybe I'd say you probably have about an 80% chance of seeing a problem like that on your AP test. So pretty common problem that is asked. Not as many points though. The other kind that you can almost guarantee that you will see in your multiple choice section looks like this, where they will provide you with a slope field, and what we are trying to do is determine which of these equations would represent this slope field. So what I like to do is if you look at these, all of these points right here gave you a slope of 0, just like all of these points here gave you a slope of 0. All right, so I like to start with those because that will help you eliminate a lot of options. All right, so I like to factor these two also. So y, I can factor out a y there. I can factor out a y here. I can factor out an x here, and this one's already good. Excuse me. So this goes from -5 to 5. So each of these would be like 1, 2, 3, 4, 5. All right. So first of all of the values of y give me a 0. So when y is 0, my overall answer is 0. So what can we eliminate? Well, if I plug 0 in here for y, that will give me a 0. Same thing with this one if I plug in 0, and this one if I plug in 0. Those first three would all fit this line right here, all of those slopes being 0. Okay? But if I jump down to, let me get rid of that so it's out of the way. There we go. If I jump down to these bottom two, do you see if I plug 0 in here for y? Oops. Man, I'm messing up a lot here. There we go. If I plug 0 in for y here, do you see that this does not necessarily give me a 0? It gives me x times 1. So, you know, like at this point right here where x is 1, we would have a slope of 1, which I don't have. So I know that is not my answer. So D is out. E doesn't even have a y coordinate to plug into, so you know E is also not the answer because there's no y coordinates to give me a 0 there when all the y's are 0, so E is out as well. So now I'm left with, I'm going to erase this, I'm left with options A, B, and C. So let's move on to the other zeros that I notice here. All of these values right here are 0, so whenever x is negative 1, I have a 0. Everybody see that? So if I plug a 0 in here for x, I'm sorry, if I plug negative 1 in here for x, that's not going to give me a 0 everywhere. So that one is out. If I plug in negative 1 for x here, that gives me y times negative 2, which again is not 0. So that one is out, and let's just make sure that it works for C. If I plug in a negative 1 here, I do get a 0. And then what you also want to do is test another point just to make sure we didn't make a mistake somewhere. So let's say if I choose this point right here. Okay, this point right here that I have filled in with blue. Actually, let me circle it because I don't want to cover it up. This point right here. That is the point 2, 1. So if I plug in y is 1 and x is 2, I get a slope of 3. That looks good. That looks like a slope of 3. And you can also check, like, let's say if we use this point, that has a y coordinate of 1 and an x coordinate of negative 2. So that would give me a slope of negative 1. That looks good. So I've tried a couple of points, and I can verify that C is the correct answer here. Next, sometimes, so if we look at this, let me just erase everything from this slide here real quick. See how these were all given to us as the derivative function. Sometimes we could be given the original function and asked some information about it. So the slope field here is for a certain differential equation is shown right here. It says shown above, but I rearranged it, so now it's shown below, but ignore that. Which of the following could be a particular solution to the differential equation satisfying y of 0 equals 0? Now, let me just show you something how this right here is useless information. Because if I plug 0 in for the x's, I get 0. If I plug 0 in for x here, I get 0. If I plug 0 in for x here, I get 1 minus 1, which is 0. Same thing here. So these all fit that criteria that y of 0 is 0. So that piece of information actually does not help me at all. Okay? So now, excuse me, what I want to do is I want to look at this is another way you could do these type of problems. You can just say, all right, if I were to follow a slope, do you see how this kind of looks like this? Okay, getting very close to 1, I'm sorry, negative 1. You can see that there is a horizontal asymptote there at negative 1 because the slopes at negative 1 were 0. Okay, so if you remember what these graphs, so x squared minus x, that is a parabola, right? So if I do x squared minus x, that's going to be a parabola of some sort. Negative sine x is, let's see, sine x goes like this, so the negative sine x would just be backwards of that, so it would come down, up, down. But you can see here that this had horizontal tangents at negative 1 and 1, but I don't have that there with the 1. Now the exponential functions, which I know you guys did not do a whole lot of graphs, if any graphs with those, remember your exponential functions start out looking like this. Okay? the minus 1 right here moves it down 1. So instead of approaching 0, that's now approaching negative 1. So here's negative 1, so it's going to kind of look like this. All right. And the last thing that we need to look at is this negative. So the negative x is what will take that and flip it over the y-axis to make it look like this. Okay? Now, the last thing that we notice is the only difference in these two is one of them is just a negative x and the other one is a negative x squared. This right here is always positive. Negative x squared is always positive. So when I plug a negative, plugging negatives or positives in here, x squared is always positive. Putting a negative out front makes this always negative. So if I have a number raised to an exponent that's always negative, remember that is a number that is always less than 1. That's a fraction that's always less than 1. Moving it down 1 like this would make it always less than 0. But you can see here in the sketch that I drew, I have some values that are above 0. So that one is out, which means C would be the correct answer. And again, if you're not sure about the exponential and logarithm graphs, that may be something that we may need to look at or talk about a little bit more. I know there's a lot of stuff online. You could look up different graphs about exponential and logarithms. But that's kind of how we would handle that. Your other option for solving this type of problem, I'm not going to go through it, but the other option that you could do is you could just take all of these functions and take their derivatives and then plug in the numbers like we did in this problem right here. So dy dx, like this one, you could say is 2x minus 1, which when you plug some numbers in here, like negative 1 for example, if I plug negative 1 in for x, I get negative 2 minus 1, which is negative 3. And I don't have a slope of negative 3 here, I have a slope of 0, so that would eliminate it. So you could go through that for all of these problems here and just take the derivatives of each of them and see which of these would fit and do the problem just like we did in that last one. So that's another way you could solve those problems. Okay. So I put a worksheet on Classroom with some problems for you to try. Hopefully you have if you don't have a way of printing them out, that's fine. Maybe you can do them digitally. But I know there's the problems all look kind of like this one. I stole the graph from this this example that I used. I stole that graph from that worksheet. So if you can print them out so you have this little slope field graph paper, you can do that, or you can just do it digitally. Like I said, it doesn't really matter. Whatever works for you guys, you can just do whichever. So yeah, I did put some extra problems here at the end if you're looking at the notes and wondering why I'm not doing them. That was basically just another 2 more examples of doing what we did in example number 1. So I'm not going to go through those, but I do want to point out one thing is, like, if we look at this second example, anytime we plug in a y coordinate of 0, we're going to have an undefined. I've seen this done 2 ways. The way that I see it done more often is that all of the y coordinates that are 0, so basically the entire x-axis, would be missing slopes, right? So if I look at what that would look like, all of your values at 1, 2, negative 1, negative 2, they wouldn't have anything. But I've also seen it where, since we know that 0 on the denominator is an undefined slope, that is a perfectly vertical slope, you could have some perfectly vertical lines there at those coordinates as well. Okay, I've seen it both ways. So when you do your AP practice problems and stuff, sometimes they're perfectly vertical lines and sometimes there's nothing there whenever we have an undefined slope, like we would here whenever the y coordinates are 0. Okay, so I just wanted to point that out to you. So like always, if you have any other questions or anything, please let me know and I will get back to you.